Navigation is an excellent example of a computationally hard problem that AI can help solve more efficiently.
What do you mean by computationally hard? Problems that have a high time or space complexity?
Yeah, precisely. Let me illustrate. I'm trying to plan a road trip from Manchester to Sheffield in the UK, and for that I wish to find the shortest path between them. Given information about where different cities and towns are located and what roadways connect them, can I use a computer to do the hard work for me?
Well, sure, this seems like a simple search problem through the graph of city nodes connected by road edges. Breadth-first search can handle that, right?
Yeah, but look what happens when I apply breadth-first search. It starts considering all the possible paths out of the source city till it reaches the desired destination on one of those paths.
Huh, that's not very efficient, and you're only showing major roadways. If you consider smaller streets and alleys, I'm guessing the space of possible paths to search can easily become intractable.
Right, and that's where AI comes in. Tell me, if you were manually planning this trip, how would you approach the problem?
Well, I can see that Sheffield is to the east and slightly south of Manchester, so I'd probably only consider the few major roadways that are coming out in that direction. Paths that I see going too far away from my destination, I might just ignore them or keep them aside to be considered later. I would definitely give priority to paths that I can see are getting me closer to my destination.
There you go. That's a perfectly fine heuristic to use.
I don't know how to drive stick, actually.
Heuristic.
Oh.
That's AI for smarts. Basically, a heuristic is some additional piece of information, a rule, function, or constraint that informs an otherwise brute force algorithm to act in a more optimal manner.
I see, but what I just described seems too imprecise to be factored into a real algorithm.
You'll be surprised. Let's draw a straight line between the source and destination. This is the shortest possible path we could ever take if the two cities were directly connected.
Right, as the crow flies.
Yeah. Now, let's consider taking a random step in any direction. The new direct distance to the destination has changed. In fact, it has become greater, which means we have effectively gone away from the destination. Let's consider a different step.
This time it looks like our distance has shrunk, so we've moved closer to our goal.
That's right. We keep testing all possible next steps from the current position and pick the one with the smallest direct distance to move to next.
One thing you haven't considered, though, is that it seems like the current next step that seems like the best choice may not turn out to be on the optimal path.
Ah, good catch. Note that we are only using our direct distance heuristic to decide which step to explore next. We're not really throwing away the other possibilities, merely storing them for later consideration in case none of the more promising paths works out.
Okay, so this helps us prioritize how our algorithm considers and evaluates different possibilities. I can see that it may prevent some unnecessary searching, but how effective is it really?
Well, let's run it and figure out.
Neat. It does seem to explore some additional paths, but it converges on the optimal direction pretty quickly.
Yeah, the exact method here is called A-star search and is one of the most popular yet effective AI algorithms out there. We'll learn more about it in the search lesson.